of all, thank you, Kiran, for wonderful introduction. And I would like to thank the organizers, especially Murali Reddy sir and Vasagam sir. Also, I can see our four, what you can say, founding fathers of Indian space program. So they all are here. So it is really privileged to be among with all of you. I will be talking on spacecraft RF characterization. But when I saw the gathering that mostly students and young professionals they are going to be there, then I thought that before going to that, I should also talk about why space is a very uh, lucrative business as well. So this data, what I'm showing is 2018 data, but still it is meaningful because now it is much more lucrative. So if you can see the global space industry is almost $335 billion. And out of this $335 billion, the satellite industry alone is $208 billion, almost 70%. And in this also, major chunk comes from the services in the form of telecommunication, earth observation, science, and national security. So what I wanted to convey is this is the place where you should be working. And if you are planning to build startups in the space, this is the right time because now this industry is growing exponentially and you can really do uh, wonders because all the space agencies, including from India, they are more and more cooperative with students, young professionals, and startups. And this is the message what I'm giving is not from my side. In fact, you can see there is a space race in the Silicon Valley where all the who's who is starting from Google's Larry, SpaceX, Elon Musk, Jeff Bezos of Amazon, as well as Facebook, Mark Zuckerberg, they all are pumping money in the space business because they see that future is space. So this is the reason why all are now moving towards the space industry or satellite industry. With this very brief introduction, I would like to go to my formal presentation where I will be talking about the spacecraft RF characterization, which includes introduction, antenna characterization, payload characterization, and then I will be concluding my presentation. So very briefly, I have characterized successfully 50 satellites and more than 350 antennas and radome. And when we talk about the RF characterization of the satellite, what kind of test we perform on the satellite? First and foremost, polarization verification of the antennas, radiation pattern measurement of all onboard antennas, and we will be finding out whether any beam shift is there or not. Additionally, spacecraft body effect. These are the antenna parameters. When I am coming to the payload, then EIRP, SFD, and G by T. EIRP is effective isotropic radiated power, SFD is saturation flux density, and G by T is gain over temperature. So this is the figure of merit of transmit as well as the receive chain of the payload. Then another very important aspect is passive intermodulation product, auto compatibility and tracking verification in few of the satellites where onboard tracking mechanism is involved. So these are the few of the satellites. Just wanted to show you that how different kind of antennas look when you see a bigger satellite rather than nano satellite which we were discussing. So you can see this is a kind of unper level antenna. This is segmented reflector, shared aperture. These are called dual gridded reflector antennas. This is a single shell reflectors. There is no gridding involved. And then you can see these are body mounted antennas. This is a navigation antenna. And then here is a short backfire antennas, again shared aperture antennas, and then multi-beam antennas. So this slide just shows you that how different kind of payload antennas look like and how bigger satellite looks like when they are put in the compact antenna facility. Now, you should know that in satellite application, it is desirable to characterize antennas at several levels, especially two levels, subsystem level and integrated spacecraft level. you may ask question why it is required when I'm doing antenna level testing, why again it is required to perform an integrated spacecraft level test. This is required to verify the mounting of all antennas on the spacecraft, because you should be aware that when any communication satellite you are putting in the geostationary orbit, satellite will be looking towards the equator. Now, when satellite is looking towards the equator, your antennas also will be looking towards equator. But if you see the any global map, equator, very few countries are there. So suppose you have to map India, you have to go from equator 22 degrees north. If your antennas are looking towards equator, it means you are not able to communicate with India. Then how you can communicate with the India? Even though satellite is looking towards equator, by providing a mechanical bias to the antenna, you can always communicate with Indian mainland. So these are the reasons why there will be mechanical biases provided on each of these antennas so that they can look towards the respective edge of coverage. So this is the first thing. By RF means we will be verifying the mounting of all the antennas. Additionally, we have done the testing of antenna alone, but when we are mounting the antennas on the satellite, what impact is created by the spacecraft body, that also we need to know. So we have to see that the spacecraft body is not inducing any disturbances on the previously measured antenna alone. If it is not happening, then we have to modify the design. Third and very, very important thing is we have to ensure that there is no degrading impact because of spacecraft environmental test on antenna or the payload. What are those spacecraft environmental tests? Like thermovacuum, vibration, and acoustic test. So any satellite, when it comes to us, before coming to us, it will go to thermovacuum, then vibration, and then acoustics. These are very, very severe tests which can change the performance of the subsystems, especially the mechanical systems. After vibration, there will be loosening of the waveguide joints. There may some crack may happen. So these are the causes where antenna or payload performance may degrade. So we have to verify those things also. So this is a typical, what you can say, antenna technology, how it progressed across globe. Initially, we used to have a Gaussian pattern where you can see circular footprint will be there. If we have to cover India, there will be a circular footprint. So you can see the mainland is here and nearby there are ocean, but still we are covering. So this is a sheer waste of the RF energy in the ocean. What you can do, you can shape these patterns so that the radiation pattern or the footprint of the antenna is exactly the Indian mainland or any mainland where people are residing rather than in the ocean. So you can by shaping the reflectors, you can achieve this. Now, when we are talking about 5G, 6G and beyond, then again, their data rates are going to be very, very high. When we are going to have data rates very, very high, we have to increase the EIRP. How we can increase the EIRP? By increasing the gain. Gain, how we can increase? By simply increasing the size of the antenna. But that liberty is not available in the satellite industry, because before launch itself, because of the launcher capabilities, there will be only finite volume available for you to make the satellite. So satellite dimensions are prefixed before launch itself. When satellite dimension is fixed, my antenna dimensions are also fixed. My antenna dimensions are, when it is fixed, how we can increase the gain of the antenna? By designing this multiple beam antenna, by retaining the same size of antenna and focusing the energy in a very small portion of the land, still we can increase the EIRP of the antenna and we can meet the requirement of 5G, 6G and beyond. So now when we need to test these kind of antennas, we require a facility which can create excellent quality plane wave. We should have a very low cross wave levels, highly accurate positioning system and highly sensitive receivers. Then only we can test this kind of very, very sensitive payloads. So this is one typical facility. We call it as a compact range, where we can use and we can simulate the ground station to the geostationary orbit or even interplanetary mission or even low Earth orbit distance by using these two reflectors, and we can create a plane wave. Because what is happening, plane wave conditions are desirable to do this test. You know, when any RF energy is transmitted from the source, initially it will be spherical in nature. When it propagates, becomes cylindrical in nature. Further it propagates, it becomes a plane wave in nature. So all these antenna parameters, they are in the far field condition when waves becomes plane wave. So we have to really create those space-like conditions when waves are plane wave. How we can create in ground these conditions? So this is a called compact range. By using these two sub-reflector and main reflector, we can create space conditions for the radio frequency. Another space condition is simulation of microgravity. You know, there is in space there is a microgravity, but when I'm deploying the antennas on ground of my satellite, what happens? Antennas, they are attached with the satellite with the hinges. They are called mechanism hinges. Now these hinges are designed for microgravity, but when you are opening your antennas on ground, they will see 1G effect. So because of that, there will be a sag. Now to avoid this sag and create a microgravity condition, you have to create a microgravity compensation fixture or gravity compensation fixture. So you have to design this kind of a fixture so that you can create a microgravity. Now you can see, you know the mass of the antenna, you know the CG line passing through the antenna. You can create R equals to mg upthrust force at these antennas locally, and you can create a microgravity. And then you can mount the satellite on our positioner, and you can perform the radiation pattern test. How you are performing these radiation pattern tests? So you can see this is dotted and this is solid. Dotted is antenna level performance and solid is satellite level performance. And you can see there is exact overlap is there on the co-pole contours. It means there is no degrading impact because of the spacecraft body on the co-pole of the antenna. That's why subsystem level and satellite level results are matching. But you can visibly see that there is a change between the subsystem level results to the satellite level result when we talk about the cross pole level. It means the spacecraft body induces a visible degrading impact on the cross pole levels, which is also important from the ITU point of view. ITU is International Telecommunication Union, which gives you the frequency allocation gives you. And it defines that your antenna or payload performance should be below. So still you can see this is acceptable performance, because in the mainland of India, when I'm talking about, I will be always referring Indian mainland because we mostly design antennas for the India. So you can see even though there is a change, but none of the portion of the cross pole is coming within the Indian mainland, so it is acceptable. If this 34 dB comes within the India, then it is a problem, or if it can coming from here, then it is a problem. And this kind of facility gives you a confidence before launch itself that the performance of your antenna as well as payload, they are going to be as per specifications or not. And how I can tell that? I can tell that we have measured the performance of the antenna in this facility. This is the blue curve. And when the satellite was actually in the orbit, we have again performed the radiation pattern measurement, which is shown by this red color. So you can see when I am doing the performance evaluation on the ground, I can go to the very wide angles, but when I'm in the orbit, I can have a very limited angle, because if I'm rotating the satellite, then what happens? Beyond India, I will be going, then I will be interfering with nearby countries, which is not desired. Okay, so when we are doing this kind of in-orbit test, we will be doing in a very, very limited angles on the actual satellite, and still we are able to capture the variations. You can see there is an excellent match observed between the in-orbit condition vis-a-vis when we are doing the measurement in this facility. So this way, we substantiate that whatever results we are measuring in this kind of facilities, they are as good as the actual in-orbit performance, and the whatever results you are getting, it will be very good. So that's why this type of facilities will reduce the operationalization time of the satellite, which used to be few months, because after launch we have to do a rigorous kind of in-orbit testing, then only it was given to the customer. But now we can do all the tests before launch itself, generate the reference data, and when we are in orbit, we will do just few tests, few cuts, and if they are matching with this facility, it means everything is fine, and we can operationalize the satellite within few days. And how this we are achieving? Actually, we will be rotating the satellite at various angles, and each angles will be doing the radiation pattern measurements. You can see these are the this is scan direction and grid points. Typically, to cover India, we need -5 degrees to +5 degrees in the steps of 0.1 degrees, elevation 0 to 8 degrees within 0.2 degrees, and then we can generate this 3T kind of a radiation pattern. I was talking about mostly for the single beam. Now the situation changes when we are going and we are covering the same India with multiple beams. And when we are doing from single beam to multiple beam, what changes will happen? So you see, when we are having a single beam, so one beam will be transmit and one beam will be received. So we need only 2 feeds to simulate ground station, one for uplink and one for the downlink. But when multiple beams are there, we cannot use this concept to characterize the antennas. What we have to do, then we have to simulate those many number of ground station feeds so that we can exactly map these beams in my facility, and then only we can do the test. So you can see, rather than 2 feeds, we have to create a feed cluster and a feed setup, then only we can perform the measurements. Now, till now I was talking about antenna characterization. Now how we are characterizing the payloads. So typical communication payload looks like there will be reflector. At the receive side, there will be a pre-select filter. This is to avoid out of band signal. And then there will be LNA and mixer. LNA is low noise amplifier. This is used to compensate the path loss from the ground to the satellite. And then we will be having a mixer. Mixer is used to down convert the frequency. You know, satellite uplink and downlink signal frequencies are different, so that there is no interference. We will be uplinking the frequency from ground at the higher frequency, means 14 gigahertz, but from satellite, when frequencies are coming down, they will be at lower frequency. Why? Because higher frequencies means higher path loss, so which we can afford from the ground, because at ground there is no limitation on the power, but on in space my power is limited with the satellite power. So that's why we will always operate lower frequencies from the satellite, so that path loss is there less and power requirement is less. So that's why frequency mixers are used. Then channel amplifier, these consist of driver amplifier followed by TWTAs. TWTAs are traveling wave tube amplifiers. So these driver amplifiers are required to amplify the signal to a level so that TWTAs can function, because TWTA has a threshold. Then filters. Several filters will be used to remove any unwanted frequencies outside the transmit band. And sometimes we may need PIM-free filter also, so that we can avoid the PIM generation. Typically for KU band, transponder gain achieved from this channel amplifier, TWTAs and driver amplifiers will be of the order of 120 dB, where receiver gain is 50 dB, driver amplifier gain is 45 dB, and TWTA gain is of the order of 50 dB. First and foremost test on the satellite payload will be doing is the noise floor spectrum. This is required to verify the integrity of the waveguide joints, in turn the total satellite transponder chain. So as soon as you switch on the transponder from the downlink, if you receive this kind of a spectrum where you are not seeing any kind of a ripple, then we are pretty sure that the health of the satellite or the transponder is good and there is no loosening of the joints. That's why there is no ripples are there. So this is a very basic but very, very important test. Next test is frequency response test. Objective of this test is to measure the variation of transponder gain with respect to the frequency. You see, typically I will be allocated with some 250 megahertz or 500 megahertz of bandwidth, and then this 500 megahertz bandwidth for a typical communication transponder will be again channelized in 40 megahertz. Out of this 40 megahertz, there will be 2 megahertz of the guard band in both the directions. So effectively, we will be having 36 megahertz of a bandwidth. So in that 36 of a megahertz of bandwidth, we have to see that over the frequency, how transponder gain is varied. So that is called frequency response. We will be seeing the gain flatness, the maximum variation of the gain peak to peak value within the frequency over in expression dB, and then gain slope also, the maximum rate of change of gain with respect to frequency over specified bandwidth and expression dB megahertz. So that's what this is the typical test setup, and we have to do this test so that we will know that over the 36 megahertz bandwidth, how my gain variations are happening. Then another important test is intermodulation product. You know that for in any non-linear device like amplifier, if we will put two tones or two frequencies, they are bound to generate a third frequency MF1 plus minus NF2. And suppose 500 megahertz, each is 40 megahertz, it means I can have 12 different frequencies. So when I am having 12 different kind of frequencies, then all the more intermod product generation is possible. So we have to really test it whether intermod product is generating or not, and then we will be having this kind of a setup to perform this, where we are having multiple signal generator, in this particular case 2 signal generators, and then power will be combining, and then we will be sending, it will be reaching to the satellite, and then again down converting and reaching to this facility, and then on the spectrum analyzer we will be seeing whether a third frequency component is generated. If it is generated, it is within the band of the payload, or it is beyond the payload. If it is beyond, then there is no problem, but if it is within the payload band, then it is an issue, and we have to rectify that.
Sir, I'm really sorry for the interruption, but we are exceeding the time limit.
Yeah. So very quickly, I am going to cover. This is effective isotropic radiated power. EIRP is the figure of merit of transmit antenna. So where we will be transmitting a signal, and then it is going to the satellite and down converted and coming back, and then we will be calculating the EIRP. This is the equation. Anyway, time is not there, so I will skip this. Another important thing is saturation flux density. This is again figure of merit of receive antenna. This is the way how we can do this. So just to give you some figure, that EIRP of C band will be almost 42, KU band 52, and Ka band when we are talking about 60, and C band SFDs will be -90, 996 in that order. I talked about intermod product, but non-linearity comes from the passive devices also. If non-linearity comes from the passive devices like antenna reflector, then again PIM can be created, and that also we have to test it. You can see a typical one PIM is generated, how noise floor will look like, and we have to rectify, and then it looks like flat. Thank you. So I think next generation measurements poses challenges, but opportunity exists to solve them. Reliable measurements are possible on ground, and it can be backed by clear understanding of the requirement, analysis and simulation, and then dry run measurements. With this, I will be concluding my presentation. And the field of RF microwave and satellite is very fascinating. You can see in the satellite, you will see only antennas and payloads, because we need more and more communication. So I would invite each one of you to join this fascinating field of the satellite, antenna, and RF and microwave. Thank you very much.